Hi, everyone. Welcome to the analysis seminar. Today, we're happy to have Stefano Decio from the Norwegian University of Science and Technology, and he's going to talk about zeros of sums of eigenfunctions.
Thank you very much, Maxime, for the introduction. Thank you for inviting me to give a talk. I'm not there in person, but I will be very soon, and I'll be happy to be there. But still nice to give a talk. Usually, the most natural probably thing to talk about with this audience would be the work that I did on Stokloff eigenfunctions, but I already talked about it once with some people that were in the audience, and there are some other things, but I didn't want to bore people, so I'm going to talk about something else, somewhat an older work that I did a couple of years ago, but that I'm back to thinking about some related questions to it. So I'm hopefully you will find some interest, and feel free to stop me at any time for questions. I don't know the background of everybody here, so just yeah, and it's a fairly small, so yeah, just stop me if there's something unclear, or even if you don't understand my handwriting. Let me jump into it. So zeros of sums of eigenfunctions. What are the eigenfunctions I'm talking about? Those are the eigenfunctions of the Laplace-Beltrami operator on a compact smooth Riemannian manifold. So here's what I'm talking about. So I'm taking mg. So g is the metric, it's a smooth Riemannian metric, and m is a constant. Okay, and I'm thinking about eigenfunction of the Laplace-Beltrami operator, which I denote by delta g. So delta g phi lambda plus lambda phi lambda equals 0. Object I'm talking about, and it's a somewhat a standard spectral theory that there is a discrete sequence of eigenvalues which accumulate to infinity. The first eigenvalue is 0, and the eigenfunctions are just constants. Okay. The eigenfunctions can be arranged to form they are orthogonal. So if you normalize them in L2, they form an orthonormal basis of L2 of the manifold. Here I put a little lump to get this is like an intuition or like a guiding principle, if you will, that an eigenfunction of the Laplace-Beltrami operator sort of behaves or looks like a polynomial of degree approximately square root of lambda. And this is by looks like here I am thinking about the local properties. People that study more global properties of eigenfunctions might disagree with this statement and say that sort of actually should like somewhat of a kind of a random wave, if you will. That's a sort of a famous it's informal conjecture by Berry. But in my setting, I'm interested in local properties of eigenfunctions, and then the polynomial of degree approximately square root of lambda is the sort of the right object, it seems to be in many situations. In particular, the object I want to study is the zero set. So the zero set of eigenfunction, I'll denote it by z phi lambda, and this is the set of points in the manifold such that the eigenfunction is 0. And I will call it either zero set or nodal set interchangeably. It's the same thing. And the question, which is informally stated, is how does this zero set look like? And it could be from a topological point of view, it could be from a metric point of view, and there's one of one of the earliest result in this business is the Courant's nodal domain theorem, which tells you that the number of nodal domains of the nth eigenfunction is less than n, for example. We'll talk especially about metric properties in a second, and here I'm just noting that so we said that 0 is the first eigenvalue and the eigenfunctions are orthogonal. So if lambda is non-zero, the zero set is not empty, okay, because the other eigenfunctions are orthogonal to constants, so the integral over the manifold is 0, and then they do have to vanish somewhere. And the expectation is that when you take phi lambda, you consider zero set of phi lambda, and if you think of the eigenvalue as increasing, then the zero set should look more and more complicated. Okay, this is and if we think of them as a polynomial, then as the degree of a polynomial gets bigger, then the zero set should be more complicated. There's certainly more of the zero set. Okay, and so in general, this is the type of result I'll be interested in. I'm interested in sort of say asymptotic result as the relevant parameter is thought large enough. Okay, and then actually the question that I'm more specifically interested about here is what if instead of a single eigenfunction you take this object, which is a linear combination of eigenfunctions. So I'm taking f, which is a sum from k from m to m, say, with real coefficients ak of phi lambda k. Okay, and there's something that can be said about the zero set of such thing. Okay, so I'm taking different eigenvalues and I'm summing the eigenfunctions. Right. Yes. So first, before talking about this specific question, I'll mention I cannot talk about zero set of eigenfunctions without mentioning the very famous conjecture of Yau, which so this is about metric properties of the zero set. So Yau in the early 80s, he formulated this conjecture that if you take the d-1 dimensional Hausdorff measure, this is how I denote it, of the zero set of the eigenfunction phi lambda, this should be bounded below and above by constant times square root of the eigenvalue. Okay, and these constants depend on the manifold. So I cannot really mention anyone that has worked on this problem because it will take me too much time, but I'll just mention sort of two results. One is a big result of Donnelly and Pfefferman, not too long after the conjecture was formulated, maybe 10 years after or something like that. So this is a result from 88, and they proved that if the metric G is real analytic, then the conjecture is true, both the upper and the lower bound. It's a very influential paper. And then almost 30 years later, Sasha Logunov proved that when the metric G is only smooth, then the lower bound holds. Lower bound is true, and there is also a polynomial upper bound. So by polynomial, I mean that the bound here is like lambda to some power, to some dimensional power, which is not very explicit. Okay, but it's still polynomial. For Logunov's result, the best known upper bound was super exponential. Okay, and the lower bound is true in general. This was in 2016. Right. So now let's go to the very particular. This was as general as it gets. So now I'm gonna just give you a very simple example. So if you just take the unit circle T1, then the eigenfunctions are, as probably everybody knows, just take sine of kx, cosine of kx, and linear combinations thereof. And the eigenvalue lambda is k squared. So here I drew the circle and I plotted the zeros. The zeros, you can see that they are spaced like 1 over k, which is exactly 1 over square root of lambda. And so if you take any ball of radius 1 over square root of lambda, this contains a 0 of your eigenfunction on the circle. And now, just to remind you, the sort of the type of question I'm more interested in this setting is, what if even in this extremely simple example, what if you take a linear combination of eigenfunctions? So you take a sum from n to m of ak sine of kx, where I'm taking the ak to be real again. Well, this is sort of it's standard that you have this upper and lower bound for the number of zeros of such a linear combination. So you have a lower bound, which is n minus 1, where n is the lowest eigenfunction you take in the sum, the lowest eigenvalue, and the upper bound n, where m is the highest one. Okay, but this sort of like the fact that any ball of radius, say 1 over square root of n, if you will, contains a 0, this does not follow immediately from this. It's and I don't know. Maybe I'm wrong, but I haven't found it classically sort of this question. So what is known is a theorem that when I started to get interested in this business of studying zero set of linear combination of eigenfunction, I was pretty happy to find it's a result about 20 years ago from Gadi Kozma and Ferenc Horowitz, which is it studies this problem of zeros of linear combination of eigenfunction for the torus. So it's a generalization of the example. So what they consider is a set S, which does not contain 0, which is a subset of the integers of ZD, multivariate integer, which is symmetric. So S is equal to minus S. So it's you build this function f of x, which is a sum over frequencies in this set S of C nu exponential of 2 pi I x. Okay, where the coefficients satisfy that C minus nu is equal to C nu conjugate, because you want the real valued object. Then they can say that if you take this thing, then this has this is a 0 in every ball of radius 1/8 sum over the frequencies of 1 over absolute value mu. This is so they don't formulate it in the language of Laplace eigenfunction, but this is a linear combination of Laplace eigenfunctions, okay, on the torus. So Laplace eigenfunction on the torus is eigenvalue lambda, which is modulus of the frequency squared. Right. So this is a linear combination of eigenfunction, and then they can say that it has many zeros somehow. So yeah, let me give a remark that if you think of these as linear combination of eigenfunctions in especially high dimension, then this bound could potentially be rather bad actually, because it doesn't because an eigenvalue in a high dimensional torus can have a ton of multiplicity, and then when you sum these and you have a lot of multiplicity here, like you should actually lump them together into a single eigenvalue. The proof of this theorem of Kozma and Norewgian uses it's a short and sweet proof. I like it, but it's very particular to the case of the torus. It's an induction on the frequencies, right? And what is even perhaps more interesting is that this at least in one dimension there is a sense in which this result is sharp. Okay, so what's the thing? What's going on? So in this paper, they construct a trigonometric polynomial, one-dimensional, say with spectrum contained in two symmetric intervals around the origin in Z. So okay, say the points, the integer points in -2n minus n, with the points in n to n, such that what happens that this polynomial does not change sign. Say it's greater than 0 in an interval of length 1/3. Say. Okay, so there's a huge part where this trigonometric polynomial is a fixed sign. Okay, so it's sort of if we go back to what happens on the sphere, this is sort of very different, right? Here there's either sort of, well, here they're actually equispaced, but morally like you could think of a perturbation of these where they're not exactly equispaced, but they're close to being equispaced, and they become sort of uniformly dense everywhere in the manifold as the eigenvalue increases. Okay, while in this example, what happens is that you have a ton of zeros here, but here you have a whole huge portion, fixed length, independent of the degree of the polynomial, where the polynomial does not change sign. Okay, and I guess the takeaway from this example is that the cardinal, the size of the spectrum of P is so the number of points you take to build your polynomial is approximately the same as the size of the spectral gap. Okay, so the spectral gap is we start at high frequency n, but then we take essentially n points, or 2 n points, to build the polynomial, and this is what creates this huge chunk of positivity. Okay, so let me go back to more general things. So we have these examples in mind. So let me first describe. I talked about this sort of this fact that the zeros are sort of dense in the manifold, but I only showed you the example of the circle. So, but there, for one eigenfunction, there is a very general result, and so I will try to explain to you that. For a single eigenfunction, you have this kind of statement that is so it can be proved in many ways, but it says that if you take any ball of radius constant or square root of the eigenvalue in the manifold, then this contains the 0 of the eigenfunction phi lambda. Okay, if lambda is not 0, of course, because otherwise the eigenfunctions are constant. Okay, and it's so the order in lambda is sharp. So you need to square root the lambda here, and of course the result is interesting asymptotically. Okay, for any, say, for the 10th eigenfunction, then you just take this constant large enough, and it's right. It doesn't tell you much. Okay, so there are many proofs of this result, and I will show you one that I like because it will be relevant for the rest of the talk. So what's I guess maybe I should say the chronologically the first probably the first proof is done through domain monotonicity, using that if you partition yeah, I'll just say that actually. Okay, so let me give you another proof which does not use domain monotonicity. So what I do is I take this function of one more variable h of xt, which is my eigenfunction phi lambda of x multiplied by this exponential square root lambda t. So this is I added one variable, and what I get out of it is I get a harmonic function in a product. Okay, I get a harmonic function in M across, say, in the interval -1. So now I want to suppose that my eigenfunction phi lambda is positive in, say, in a ball of radius 2r. The center is not important in the manifold, and I want and of course what I want is an upper bound on r. Okay, so let me show you how you get this. This can be done as a very simple consequence of a purely elliptic tool, which is the Harnach inequality. So I will use the Harnach inequality on this H. Okay, this is a harmonic function, and so the Harnach inequality tells me that the supremum over this set, so ball of radius r cross, say, minus r of H is less than a constant times the infimum for the same ball. Well, but then I just write out what H is, and this is certainly greater than e to the square root lambda r times the infimum over a ball in the base manifold phi lambda. And well, this is certainly smaller than, again, I carry over the constant times the infimum over a base ball in the manifold of phi lambda. What you have is this inequality. The infimum goes away, and you get that e to the square root of lambda r is bounded by a constant, which means that r has to be less than a constant for square root of lambda. This is a pretty simple proof, and what I like about this proof is that it uses essentially just the fact that this satisfies an elliptic PD. Okay, this sort of extended factor satisfies an elliptic PD. You don't really need to know anything about eigenfunctions. You just need to know the equation and the fact that when you do this little trick, you get harmonic. So the restriction that I get is what I wanted. Right. So now let me tell you what I can do, which does not necessarily coincide with what can be done, but let me tell you what I can do for more than one eigenfunction. For more than one eigenfunction, I remind you what the object I'm taking is f, which is a sum from n to m of ak phi lambda k, where let me just put it everywhere so we're clear that these coefficients are real. Okay, and so this is the notation. Maybe it's a bit confusing, but this is just the way I label the eigenvalues is from lambda n to lambda m, but this can be any sequence of eigenvalues. Okay, so this is not necessarily the nth eigenvalues, it's not the nth eigenvalues, it's just otherwise the notation gets too heavy if I keep on adding indices. Okay, but this can be confusing, so if you're confused by it at any point, please just ask me. Okay, but yeah, this is any sequence of eigenvalues. Okay, and let me call Q for simplicity the number of eigenfunctions I'm considering. So m minus n plus 1, and I take lambda n to be non-zero. So the theorem that I proved a couple of years ago is that if you have so same setting, if you have a smooth compact manifold, then this linear combination of eigenfunctions f contains a zero in every ball of radius constant over square root of lambda n. So lambda n is the lowest eigenvalue I take in the sum, and this constant depends clearly on the manifold, but also on the number of eigenfunctions I use to build my sum. Okay. And the fact that there should be a dependence on this number is clear because of this, where the example I showed you before comes through. Okay, this tells you that if you take so there must be some dependence on the number of eigenfunctions. If you take a lot of eigenfunctions, then you can create large spectral, not large spectral gaps. The spectral gap is given large gaps in the zero set. Okay, large gaps in the zeros. So my constant will have to depend on Q, and it's sort of, I think it's an interesting problem to see exactly how, and I will comment more on it. Let me sketch the proof for you, and this is probably the part where I'll be sort of most technical, so it's a good time to fall asleep if you're inclined to do so. Yeah, I think I need to give you a sketch of the proof. It's quite simple. It's a bit technical, but there's nothing too difficult that comes into it. So if you take this f, which is a linear combination of eigenfunction, then this satisfies this equation. It's a product of from with k that goes from n to m of Laplacian plus lambda k. And maybe I call this Laplace g, so let me be consistent. Okay, so satisfies this equation on the manifold. Okay, this is just an immediate computation. And then if you take, I want to do a trick similar to the one I showed you in the proof for one eigenfunction. Okay, so the most natural thing actually, and the people that have studied linear combination of eigenfunction in sort of other setting, this is what they do, is you take this f and you multiply each of these eigenfunction by the exponential with the right frequency. And then you would get harmonic function much in the same way as you get harmonic function here for one single eigenfunction, but then you sort of lose control of the zeros. Because if you multiply by exponential different frequencies, and then the zero set, it's not anymore a cylinder of the zero set of your original eigenfunction. Okay, so this is not what I want to do. What I want to do is I take this my extension h of xt, which is the linear combination of eigenfunction f of x times e to the square root of lambda n t. So I take only one frequency, namely the lowest in the sum that I consider. So I know that the zero set of this thing looks exactly like the zero set of f. Okay, just a cylinder over it. And then this satisfies another equation, which is similar to the one above. So you have you kill one frequency, so you have one Laplacian outside, and then you have product from n plus 1 to m of the Laplacian plus the difference for the eigenvalue lambda k with lambda n. Okay, and by my assumption here, I have that this is greater than 0. Or should say greater or equal than 0. Okay, so my function a satisfies this equation. What's the order of this equation? Is the equation is of order 2q, okay? Which is greater than 2, because if q is equal to 1, then it's just one eigenfunction, and I know what to do. Okay, so this equation is of high order, and there is no Harnach inequality for such things. I will show you later. I mean, you probably already know, but I will show you later. But there can be no Harnach inequality. It's just false for a higher order elliptic PDEs. So what I want to do is I want to prove some kind of alternative for Harnach inequality. So how do you? What's the solution I propose is so for that I will abstract a little bit, but say I'm thinking about L, which is an elliptic operator of order 2q, where q is greater than 1. And yeah, you need some assumptions on the structure of this elliptic operator, but the operators, as in the previous page, work. Okay, then I can say that if you take any radius small enough, smaller than some r0, and any solution, and then a positive solution of this elliptic operator in a ball of radius 4r, then what happens is you can control the integral over the ball of radius 2r of this solution by a constant depending on q, so on the order of the operator times the integral of the ball of radius r of h. Okay, so you control the integral twice the ball over the radius. Sorry, you control the integral in a ball with the integral in a ball of half the radius. Okay, so this could remind you, if people are familiar with this, of like doubling inequalities for elliptic PDEs. But what they usually do in their setting is first they have L2 norms, and then they don't assume that the function is positive. So it reminds you of this, but the spirit is a little bit different, if you will, because if you don't assume that your solution is positive, then you cannot get an inequality with constant here, which does not depend on. So this is it's the way I think of this inequality is really as some kind of a substitute for Harnach inequality. It's a fact about positive solutions of higher order elliptic PDEs. The proof is a bit technical. It's just integration by parts, because that's the only thing I know how to do. It's a higher order elliptic PDE. I don't have many tools, so that's the only thing I can do, and that's what I will do. Okay, and I'll give you a little sketch. Right. So first, let me show you how I claim that this sort of alternative Harnach inequality solves the problem of, at least partially, the problem of this density of zeros for a linear combination of eigenfunctions. So now I suppose that that my sum of eigenfunction f is positive on a ball of say radius 4r in the manifold. And I remind you what my h is just f times e to the square root of lambda n t. Then this is positive on a ball of the ball of radius 4r across the interval minus 4r, say. Okay. Then much like in the proof that I showed for one eigenfunction where you use Harnach inequality and this extended thing, I'm going to use my alternative inequality on this h. So if I write it down, what do I have is the integral over the ball of radius 2r of f times integral from minus 2r to r e square root lambda n t is controlled by a constant depending on q. I don't indicate so the constant also depends on the manifold, but I don't indicate it for brevity. And here I have the integral over the ball radius r of f integral from minus r to r of e square root lambda n t. Okay, so well, this one is clearly less than the integral over the ball of radius 2r of the same thing, so it can be, remember that the function is positive, the ball of radius 2r. So what you get again is from this is that e square root lambda on r should be bounded by some other constant depending on q. Okay.
Sorry, and what is the operator L? What is the elliptic operator used?
Right, so it's something like this.
But how the Laplacian before the bracket appeared?
It's not necessary at this stage. It's not necessary.
Huh?
It's not necessary. So I don't need that. I don't need this specific structure of the operator. But then, so from these, I get again the restriction that the radius r has to be less than a constant depending on q or square root of lambda. Yeah. So yeah, so here that's what I really use is that when I build this auxiliary function, the fact that I'm using only one frequency to extend it to another dimension means that my zero set is just the same except in one dimension. Okay, I couldn't do this if I multiplied every term in the sum by an exponential. Then I would get a harmonic function, so a nicer equation, but then I would sort of lose control in this sense of the zero set. So now, hopefully I convinced you that once I get this sort of pseudo Harnach integral inequality for higher order elliptic operator, I can prove the density statement. So what's really to prove is this sort of pseudo Harnach inequality. So I'll comment a little bit on that. And again, this is maybe slightly technical, so feel free to doze off. But what I'm talking about is an elliptic operator of order 2q, which is uniformly elliptic. So you can write it in this form as a sum over multi-indices mu with order bounded by 2q of some coefficient, say mu of x, partial mu. Okay, and the uniformly elliptic means that if it's a property of the top order part. So if you take the sum over the multi-indices with modulus with length exactly 2q of a mu of x times psi mu, then this is bounded below and above by a constant times the absolute value of psi to the 2q. Okay, this is sort of the usual ellipticity, uniform ellipticity. The object I'm talking about, and I promise you that I would tell you that that actually the Harnach inequality, you cannot just do the Harnach inequality because it's false. So the Harnach inequality does not hold for solutions of higher order elliptic operator. So if you take some h which satisfies LH equals 0, such for instance, you could take, you can think of x1 squared, the first coordinate squared, then this is a biharmonic, for instance. So it satisfies a perfectly good higher order elliptic PDE. And then what happens is that, well, this as a line of zeros, and then it rises in this way. So that if you take the infimum over ball center there, then this is 0, right? So there's no hope to control the suit with the supremum with the infimum. It's very well known, but it's good to to fix the ideas, and yeah, so that there is hopefully some content in what I'm saying. Okay, so right, so then let me try to give you some words of how I prove this sort of integral Harnach inequality. So first, let me suppose that I can find some weight VR, some positive weight VR, which has sufficiently many derivatives. Now the C2Q, so 2Q is the order of the operator. Remember, in say the closure of a ball of radius 3r, and I want the weight with these properties. So I want all the partial derivatives up to order 2Q minus 1 at the boundary of this largest ball of radius 3r to be 0. Then what do I want? I want that that the adjoint, so by L star I denote the adjoint of my operator L applied to this weight VR is greater than 1 on the, maybe it's useful to draw a picture. So this is my ball of radius 3r. Here I have the ball of radius 2r. Here I have the ball of radius r. Okay, so I want the adjoint of the operator to be greater than 1 on this annulus, okay, the middle ball minus the smallest ball, and then I want it to be positive, but with no definite bound on the larger annulus, this one, okay, the largest ball minus the smallest ball. The last property that I will require of this weight is that the supremum over the smallest ball of the absolute value of L star VR is bounded by a constant depending on the order of the operator. Okay, so suppose that this can be found, and I'm going to show you that if you have this, then this sort of gives you the inequality that you want. Okay, how do I do this? Well, okay, I can say that then I take actually any super solution. Let's say think of it as a solution. So for a solution of the LH equals 0, which is positive in the ball of radius 4r, then we have that 0 is greater than the integral of the ball of radius 3r of LH times VR, okay, because VR is positive. Well, then this is equal to the integral of the ball of radius 3r of H L star VR, okay, where the boundary terms get killed by my first property. Now, I wanna estimate the integral over the smallest annulus, ball of radius 2r minus ball of radius r, okay, of my H. And then by this property, then this is less than the integral over the ball of radius 2r minus the ball of radius r of H L star VR, okay. By this property, this is less than the integral over the ball of radius 3r minus the ball of radius r of H L star VR. Okay, this is by this line, this is equal to minus the integral over the ball of radius VR H L star. And then finally, by my last property, this is less than a constant depending on Q times the integral over the ball of radius r of H. So if you look at this and you look at this, I estimated the integral in the annulus, so estimated the integral of my H by the integral here. Okay, I estimate the integral over the ball of twice the radius by the integral over the ball of the radius r. Okay, which gives me what I want. So really, the only thing to do is to show that, and I will not show the details of these, but to just sort of convince you that you can construct such weight somehow. So the picture that I have in mind when I thought about this is that I want something. So I'll go back to the definition. So to the properties actually that I require this weight. So I want that the adjoint operator is bounded from below on an annulus. So somehow in this annulus I need something which is very convex in some sense. Or at least that's right. So the picture I have in mind, if you look at it in section, is something like this. So the way I do this technically is I start with this function, which is simply just 1 over absolute value of x to the power alpha. Okay, where alpha is some large constant depending on the order, which will be very large. And what you can show is that if this alpha is very large, then when you apply the adjoint operator L star to this v, then this is greater than this constant alpha to the order of the operator to q, and then on the denominator you have what you expect. So absolute value of x to the alpha plus 2q. I think actually something like this was used by Landis in some old papers in maybe even a book from the 60s. So he used these sort of explicit test functions to prove something that is sort of related to what I'm trying to do. So that's where I took the idea. Okay, so one can show this thing, and then one you can show when you're sort of halfway there. Once you show this thing, because then I need this condition. So I need to essentially take this function and subtract its Taylor polynomial at the boundary of the largest pole, so that I can make sure that all the derivatives up to order 2q minus 1 are 0. And then of course this thing blows up at the origin, so I need to make it not blow up. Here I drew it, so I cut it off, but I need to, it's a bit delicate, but I need to cut it off in a sort of a controlled way because I don't want to lose too much the constants. So I multiplied by a cutoff function that has essentially the optimal growth of derivatives, which is not an analytic function, but almost as good as it gets without being an analytic function. This is the cutoff that I use, and then I can build this way. And let me note something. So I have this constant CQ. So Q again is this. Okay, 2Q is the order of the operator, but it's the same. So this constant CQ has to. First of all, if you look at the proof that I wrote here, what is this constant CQ? Well, this is essentially the supremum over the adjoint of the adjoint operator L star applied to VR in the ball of radius R. And you can see it from the construction, or you can see it from explicit examples just by plugging in some polynomials, that this constant CQ has to be at least exponential. And if you think about the previous proof that I showed you, so the proof that from this density follows, what you have is, let me remark here, you had something like, e square root of lambda less than this sort of CQ, where CQ is the same here. So when I take sort of the density constant, the upper bound on sort of my positivity radius, this is essentially the log. So this tells me that let me go back to the statement of the theorem. It is a bit, but okay, right. What I want to say is that then since these constant is sort of the density theorem has to grow at least linearly in Q, to be at least. This is also consistent with the example of a polynomial, right? So here you have the number of so the cardinality of the spectrum, which is approximately n, is is a sort of the critical, if you will, density radius. Okay, but so this is just this is a lower bound on the growth of the constant. I cannot reach it. Okay, so here comes to the things that I don't know. I have questions, and some of these I'm trying to actually think about sort of now or in the near future. So one question is, how actually does this constant grow in Q? One would expect that, for at least from the compositions that I do for a real analytic metric, I do expect to get the sort of the linear growth of the constant, which should be optimal. I thought this would be easier, but the sort of the combinatorics in the proof I use a lot of derivatives of this weight, and I lose track of it at some point in the combinatorics. So I have some bounds, some quantitative bounds in Q for the constant, but I cannot get to the linear one. So I sort of dropped it. I think it should be possible, but
Stefano,
yes,
on the two sphere, what
yes.
is something known, like you know, something more explicit, like on the
I
torus,
don't know actually. I don't know if there's. I tried to look for it a while ago, but I don't know. It seems actually even because yeah, it's probably it's probably a quirk of my proof that even even if I think of it as the standard Laplacian somehow, if the computations since I have to take many derivatives of this weight function, they get complicated. And I don't know if something was known. I don't think people really studied this problem on the sphere somehow, but maybe I just didn't find it.
Okay. Thank you. Yeah, no, I guess the question is, can you replace like trig polynomials in that explicit sharp example on
Right.
on the circle by some Jacobi or something like that?
Yeah. I think it could be possible. I haven't done it and I haven't seen it done. I guess that's the honest answer.
Okay, thank you.
It could be possible. Yes, I shouldn't be surprised. Okay. So another question, which is maybe more interesting, if you will, is that if I think it should be natural, and I think there should be hope to get like a better constant if the spectrum is sparse in some way. Okay, so here, like my theorem is essentially you take any sequence of of ordered eigenfunctions, and then what if what if I take I start still with a spectral gap. But then the next eigenvalue that I take is way larger, and then again, so it's something like a lacunary sequence or something like that. I think morally the eigenfunctions should oscillate on very different scales at this point, so they should influence each other less, and you should get something better. I think this should be possible. I haven't done it yet. It's something I think it could be worth to think about. And then another question, which is also potentially interesting, I think, what if you take, instead of taking a deterministic eigenfunction where these are real numbers, then you take a random linear combination of eigenfunctions. Okay, there's in recent years, people have studied a lot of linear combination of eigenfunctions. So the question I propose in this setting, if you take this f, which is just built as a linear combination of eigenfunctions with Gaussian coefficients, say, is it true that that you essentially have the same result as for trigonometric polynomials, which should be plausible? So is it true that f has a 0 in every ball, say, of this radius, sum from n to m of 1 over square root of the frequency, 1 over square root of lambda k, with high probability? Even with probability, I don't know. Yeah, say we probably do 1 minus epsilon for every epsilon. I think this is a fair question. It might be easy for people that know how to do this, that know how to study a zero set of random eigenfunctions. Usually, people concentrate more on like the homogeneous case, so they fix a window about one eigenvalue, and they take linear combinations with of eigenfunctions with eigenvalue in that window. So eigenvalue very close together. Here I'm saying something. I'm taking the eigenvalues here can be quite far apart. Okay. So this is actually the density, the sort of the right density radius that would come from at least one-dimensional trigonometric polynomials. So you could do maybe something simpler, which is close to my setting, which is substitute this by q over square root lambda n. So getting sort of the linear bounding q. Okay. I think probably the difficulty is sort of the same though. So I don't know if this is, it could be that this is an easy question, but I would be interested in knowing the answer if you can say this with high probability. And then, you could ask what is the expectation of, say, then on the inner radius, if it's, if you can say that the expectation is actually this thing. So for the radius of the largest ball. And you could, this is probably a bit more difficult to try to compute variance estimates on this in the radius. Say, actually, how much does it deviate on average? Okay. So I'm almost done. I will just finish by mentioning some other things that I don't know. So it's this has been 15 minutes of things I don't know, which is it's not. It's sometimes it's nice. So because if you're interested in Hausdorff measure bound on the size of zero set, then this sort of density statement is the first step in getting a lower measure bound in the conjecture of Yau. Okay, you first find to say that the measure of the zero set has to be large enough. Well, it's useful to first know that there are a bunch of zeros, that there are a lot of zeros, and namely that there are zeros in every ball of radius constant over square root of lambda. Okay, so once you have these, then it's not easy. It's extremely hard. That's what the Sasha Loganov did in 2016. But you can get, using this density of zero, you can get the lower bound in Yau's conjecture. You can say that the measure of the zero is greater than a constant times square root of lambda. Okay, but let me say that actually in 2D this is extremely easy. So in 2D, the only thing you need to know to prove the lower bound in Yau's conjecture is essentially the density of zeros. Okay, because in 2D what you have, okay, you have all of these balls where you have a zero of the eigenfunction at the center. You take this ball. Well, the maximum principle tells you that there are no loops inside this ball, so the zero set has to exit this ball. Okay, and then we're in 2D, so essentially plane geometry tells you that that the length of this curve is longer than the diameter, so it's bounded from below by a constant, and you have a ton of these balls with these atoms. Okay, so in 2D this is I think this was somehow the argument of Brüning. To put a name to it, something like 70 something, 73 maybe. But this was known already when Yau formulated the conjecture, I believe. Okay, so in 2D this is easy for one eigenfunction. You don't need the sort of deep result of Sasha Loganov. But for linear eigenfunctions, I don't know it. And for linear eigenfunction, the only thing I know is in 1D actually. In 1D, there's an even stronger result. So if you can even take like an infinite sum of eigenfunction with a large spectral gap. So you sum over k, such as k squared is greater than lambda of ak sine of kx. And then the number of zeros of f is greater than a constant times square root of lambda. Okay, this is what in higher dimension there seems to be, or at least the way I see it, the problem is that you can see it already on the sphere, already on the two sphere in R3. So the eigenfunction is spherical harmonics, and you can build a sum of two spherical harmonics. So I take, for instance, I take the zonal spherical harmonics. What are those? Those are eigenfunctions that say that have a peak, a large peak at the North Pole. Okay. Then you sum two of these with different eigenvalues. Then you can have an isolated zero if you tune these two coefficients. And if you have an isolated zero, then you can actually make like a pool of zeros, a loop of zero that is as small as you want it. And if you have this sort of density of zeros, the measure could be extremely small a priori. Okay, so that, in my opinion, that's the sort of what makes it hard to get a lower bound for a linear combination of eigenfunctions, even in 2 dimension, where for one eigenfunction it's easy and it's just a consequence of the density. I would be happy to get some result. And what is true is something that is weaker. So. But for more general things, so you take the people have studied the linear combination of eigenfunction again with a spectral gap. So they're starting at eigenvalues lambda j greater than some lambda, and then they can bound from below the measure of the zero set by what you expect, the square root of the eigenvalue. But then there's also these factors that depend on the norms. So it's a ratio of the L1 norm squared by the L infinity norm, and this thing can be huge. It's actually, even for a single eigenfunction, like for a single eigenfunction, we don't have this factor. That's proof of Sasha Loganov. For in 2D, it's easier. So that makes me think that this factor should not be there, because even for a single eigenfunction, this one can be quite large actually. In more than one dimension, in one dimension, no, but in more than one dimension, this factor can be large. So my question is as follows: just as simple as you could do it, just take a sum of two eigenfunctions, a phi lambda plus b phi mu, say where lambda is less than mu, and can we get the lower bound of the Hausdorff measure of the zero set of f, which is the order you would expect it without this dependency of the ratios of the norm? I think this should be true. I wouldn't be entirely surprised if it's not, but yeah, there's work that needs to be done, I think, in understanding. Like once you have zeros, you can have this very small loop of zeros, but you shouldn't have too many small loops of zero. Like somewhere you should have large portion of the zero set or something like that. This could be true. Yeah, and this is all I wanted to say. Thank you for bearing with me, and I'm happy to take questions should there be any. Thank you.
Thank you, Stefan. Are there any questions?
So I have a question about the sort of the applicability of the method. So it's kind of interesting that you are proving some sort of an analog of Harnach for higher order operators. So there is a question that I personally find very interesting about density of nodal sets for eigenfunctions of say biharmonic problems like the clamp split problem. I'm wondering if that might apply this idea.
All right. So the problem it's a problem of sign. So at some point in my let me go back to right. So at some point in my equation, I had this that I sort of swept under the rug, but I mentioned that this sign is positive. The problem is that the biharmonic has positive eigenvalues, and then it sort of screws up the argument. So I can prove density of zero set for like the Laplacian to the third with the exact same argument, or any odd power of the Laplacian. But with this thing, I cannot prove density of zero for even power of the Laplacians. We can talk more in a bit more than a week, and I'd be happy to discuss it. But yeah, it's a very fair question, and yeah, it's interesting. But yeah, not immediately. I cannot get it. Yeah,
it's an old question. We wrote a paper once with Dan Mangubi where we asked, how well can you approximate a typical point on a manifold by zero sets of eigenfunctions, pure eigenfunctions, not just linear combinations. And why is it somewhat interesting? Because if you take interval and put, let's say, Dirichlet boundary conditions, then zeros are just rational points, and then best approximation is continued fractions, which is kind of fun. Now, what is continued fractions on a general manifold or on a domain? What can you say? But we did some sort of very obvious things, but I think it's a somewhat interesting question as well.
Okay, thanks. I should take a look at it.
Yeah, for things like fractional powers or like half integer powers, it's probably you have to think of some other thing, right?
I think so. Yeah, it's it's a little scary to think of. I mean, I studied sort of the analogous problem for Stekloff eigenfunction, this density of zeros, right? And there it's like if you think about eigenfunction of the Dirichlet Norman operator, so if you're on the boundary, then there are some weird things that can happen. Okay, it's not the most, but if you take a rectangle, then there are like two sides of the rectangle with no zeros at all.
Yeah, okay.
For eigenfunction of the Dirichlet Norman operator. So this is like it's quite non-local. So it's okay. I think somehow but my argument here is very local.
And you work with polynomials, so is there any hope for any kind of power series in the Laplacian to have some sort of Harnach, let the coefficients decay very fast or anything like this?
Yeah, this is probably maybe connected to what I was asking about, sort of like if you take Lacunary
and for Lacunary trig polynomials, is there anything better than just general, or there is nothing much?
So it's I actually so I gave a similar talk in Tel Aviv recently, and then I talked a little with Gadi Kozma, and he said he didn't know much. Like he had when they wrote this paper, they had some questions also about Lacunary sequences and say whether this is better for them, and but yeah, I don't think they found an answer.
Are there any upper bounds known for the length of the zero set for sums of eigenfunctions?
Yes, so it's essentially if the metric is real analytic, you have the same as Donnelly-Pfefferman. So you have the upper bound, which is square root of the highest frequency, and this is done actually like what I was saying is you take this f and instead you multiply by an exponential at every frequency, then you get a harmonic function, and then there's I mean, Fangualin did something like this, and then there's a paper by Jerison and Lebeau where they do this, and they essentially extend that. So they use Carleman estimates methods of Donnelly and Pfefferman, and they get the upper bound also for linear combinations. And you don't need to start high in the spectrum. You can start from the constant, say it's sum them up to lambda, and then you have an upper bound of constant square root of lambda. And then in the smooth, I would expect, I would expect that you have, the same bound as we have for one eigenfunction, so polynomial, and the eigenvalue. So you probably can replicate such a. Okay. Yes, I think you can. I don't think this is written, but I'm pretty sure you can. But yeah. Okay. That probably is worth it to expect to get the sharp bound for one eigenfunction in the smooth case.
I'm not sure I followed your argument for how to pass from density of zeros to lower bounds on the length of the zero set. Could you just repeat?
Yeah, the one in 2D you mean, right? Because it's in 3D and longer it's and more it's a lot more complicated. But yeah, in 2D, right? So actually, let me go to another page. That's easy. Okay, so what you have is you have balls. The radius of this ball is constant over square root of lambda. So you have lambda to the d of lambda to the d over 2 balls in the manifold. Okay, with zeros. So you can say that you have approximately lambda to the d over 2 balls with zeros in the center. Okay, so you have an eigenfunction. So you localize to any one of these balls. So we are here. We have the ball of radius constant over square root of lambda with an eigenfunction that has a 0 in the center. And then you can either think of the harmonic extension of the eigenfunction, so multiplied by the exponential, so that you get the harmonic function, say in some kind of a cylinder, and then use the maximum principle there. Or you can just rescale the ball, and you get the equation, say Laplace phi lambda tilde plus I don't know, epsilon x phi lambda tilde in a unit ball, where this is much smaller than 1. So anyway, this is just to say that you can use the maximum principle in this ball, or like a weak form of the maximum principle in this ball, which tells you that then you cannot have like small loops of zeros, right? Let me know if this is unclear. I'm happy to.
And I guess so. You can have loops, but you're saying that they cannot be small, or
right? Exactly. So the radius of this ball is constant over square root of lambda. You can definitely have loops. So say these are the balls. You can have large loops, but inside the ball of radius constant over square root of lambda, if this if you restrict it such that this constant is small, you cannot have loops inside. So what happens is you have to exit the ball, and then the length of these has to be greater than the diameter, right? And you do this for so the length of the zero set here is greater than lambda. Okay, this is very difficult, but square root of lambda to the 1 minus t, right? In each of these balls, you have a bound which is this. It's like the diameter, and then you have lambda to the d half balls, and then you get square root of lambda.
Seeing how you are applying the maximum.
Yeah. So you need to be in these small balls of radius. Yeah, then it's and either you think of the harmonic extension or just a rescaling.
There are other questions or comments. Okay, let's thank Stefano again.
Thank you very much.